Okay, this is the first of a number of videos we're going to do that's going to start to create some vocab cards. So the vocab cards are just blank index cards. They'll be 3-hole punched. If your cards don't happen to be punched, please see me and I'll help you figure out how to do that. And then we're eventually going to put them on a big metal ring so that we're going to have kind of a whole flip list of vocab cards. And the purpose of these cards is for us to prepare for the semester or the final exam. It's going to review lots of topics, lots of ideas. It also will be a resource for you over this next month to review and practice for the M step. So you're going to want to hang on to these, and the metal rings are designed so that you can clip them right in your 3-ring binder so that they're not lost. Okay, so vocab card number 1, you're going to start out with this, and feel free to make this your own. And what I mean by that is if you want to grab highlighters or different colors of pen to add color, you can do that, and you can pause the video at any time. So the first vocab card, the topic is integers. And integers is one of those basic words that you're going to need to know because many of the semester exam questions or M-step questions will say find the integer. And if you're not sure even what an integer is, you might give your answer as a decimal or as a fraction, and those are not integers. Integers are only positive and negative whole numbers. So this graph is showing -3, -2, -1, and we're putting solid dots on all the integers. Integers do not include fractions or decimals, like 1/2, right here. 1/2 is not an integer. 0.6 is not an integer, just positive and whole numbers. Positive and negative whole numbers. So if you need to pause the video to complete that, please do that. And our next card, we're going to divide into 2 parts. The first part has to be much bigger than the second. So we've got rational numbers and irrational numbers. So let's talk about rational numbers first. Rational numbers are numbers that can be written as A over B. And A over B is just a fancy, general mathy way of saying that they can be expressed as a fraction. So integers, like the integer 12, is also a rational number because we can express 12 as 12 over 1. So all integers are rational numbers. So -3 is an integer. -3 would be considered a rational number because that's written as -3 over 1. Obviously over here, if something's just a plain fraction, it already is in rational form. It's rational. A mixed number is a rational number because we can change that into an improper fraction and it's in the form of A over B. But there's 2 other types of numbers that are also rational, and that's any decimal that terminates. So remember, a terminating decimal is a decimal that comes to an end. So 0.75 can be turned into 3/4. Also, any repeating decimal, like 0.3 repeating, is 1/3. And if you remember, we did a whole activity when we did something like this, 0.7 repeating. Remember that was 7 was the numerator and 9 was the denominator. That generated 0.7 repeating. So any repeating decimal is rational. Any terminating decimal is rational. So the opposite of rational is if we put the prefix IRR in front of it. Irrational means cannot be written as a fraction. It cannot be written in the form of A over B. And the only things that cannot be written as a fraction are never ending or never repeating decimals. And the one that you're most familiar with is the number pi. Pi is the most famous irrational number. It never repeats, it never ends. And mathematicians have tried to say that the fraction 22/7 is pi. Well, if you try that on your calculator, 22/7 is a fraction. It would make it a rational number. But if you actually do that on your calculator, you'll see that it's not exactly pi. So there's no way that they've come up with a way to express pi as a fraction. So it's called irrational. Okay, the next one, and I'll do this one with you, is absolute value. Absolute value we talked about at the beginning of the year. An absolute value is a number's distance from zero. A number's distance from zero. Okay, so if you draw a quick number line, and we're going to put 0 in the middle, and let's pick a negative integer. So down here, let's do -8. If we had to measure the distance that -8 is from 0, remember we talked about distance is always positive. So you can't say it's -8 feet from 0. That distance is +8. If the number is positive, like 3, its distance from 0 is 3. Okay. The notation for absolute value is we use two kind of field goal symbols, straight up and down. We enclose the number with straight lines, and we would read this, the absolute value of -8, meaning the distance that -8 is from 0 is 8. The absolute value of 3 is the distance that 3 is from 0, and that's 3. Okay, so with this, a couple of errors that kids make is they mistake these symbols with something like this. If a publisher of a test or a book uses parentheses to enclose a -8, that means absolutely nothing to do with absolute value. That is just a way of kind of distinguishing or setting apart -8 so that you can see it better. So you may see it in a problem like this. -8 plus 3. This does not mean the absolute value of -8. This is just a way of kind of bringing your attention to that -8 symbol. Okay, so a couple problems we want to do is what happens if you use the absolute value in some sort of an equation like this. The absolute value of -7 plus the absolute value of -4. Well, you first have to figure out each of these absolute values. So the absolute value of -7 is +7. Absolute value of -4 is +4. This comes out to be 11. Okay, so let's try something a little bit different. What if we saw this? And what if the math operation was inside of the absolute value symbol? Well, remember with our order of operations, you need to do inside any parentheses or any grouping symbols first. So we really have to do this calculation first. So apart from the negative or the absolute value, what is -8 plus 3? So we think about who's going to win the war. The negative team has 8 people. The positive team has 3. So they're going to go to battle. These 3 positives are going to kill off 3 negatives, and we're left with -5. So inside the absolute value symbol, we got -5. So now we do the absolute value of -5, which is +5. Okay, what do you think the biggest error is when kids see this problem? Well, kids see these symbols and they say, oh, it turns everything positive. So this is 8 and this is 3. 8 plus 3 is 11. And as you can see, that's not the solution. And the problem is, if you do that, you're not following order of operations. This calculation must be done first before you apply the absolute value. Okay. The next one is additive inverse. And I think to save space, we're going to do additive inverse and multiplicative inverse on the same card. Okay? So the reason we're highlighting this is that we are going to do some activities with these cards, and if you can recognize what the topic of each card is with the highlighters, you'll be able to find the solutions a little easier. So the idea of inverse is that it's something that is going to undo. Okay, so if I do the inverse operation of putting my shoes and socks on, well, in the morning when I put my socks and shoes on, don't I put my socks on first and then my shoes? And when I come home, I do the inverse operation. When I come home at night, I first have to take off my shoes, then take off my socks. So inverse means to undo something. So we want to think, what undoes adding 5? So if we have 5 in a problem, how do we undo adding 5? We add a negative 5. So we would say that 5 and negative 5, since they add together to get us back to 0, are called additive inverses. So if you add m and negative m, those two things are going to undo each other. Okay, so how do we think about this in a problem? If our problem is x plus negative 7 equals 14. Remember, when we solved equations like this, we wanted to think about what operation would undo adding negative 7. So we think of the additive inverse. So what would make negative 7 become 0? And that's if we add positive 7. So these two things, we zero them out because they are additive inverses. They undo each other. And if you add 7 here, you add 7 here, and these are gone. And we get x is equal to 21. So that's how we apply the idea of additive inverse. Okay, so let's do the same thing with multiplicative inverse. If you multiply something by 2/3, what can you multiply to undo 2/3? To undo multiplying by 2/3? Well, the multiplicative inverse is the reciprocal. Because notice what happens. If we start with the number 1 and we multiply it by 2/3, if we then multiply by 3/2, notice that the 2's are going to cross reduce, the 3's are going to cross reduce, and we're right back where we started with the number 1. So multiplicative inverse, another name for a multiplicative inverse is reciprocal. So let's find the multiplicative inverse of negative 1/7. What would the reciprocal of negative 1/7 be? Well, you flip it to be negative 7/1. And when you multiply those, the 7's are going to cross reduce to a 1. Negative times a negative is positive. You get positive 1. Okay, so let's see how this worked in a problem. If you remember, if we had something like this, just making this up off the top of my head, so it might not work out real well, but 5/6 times m equals 12. To solve this equation, we need m to become just 1m, not 5, 6m. We want this to cancel to 1. Well, over here, we learned how to cancel a fraction to 1 by multiplying by the inverse. So we're going to multiply on this side by the inverse of 5/6, which is 6 over 5, and we're going to multiply this by the inverse, which is 6 over 5. Notice that these are all going to cancel, and we're left with m equals, let's see, 60, no, not 60, it's going to be 72 fifths, because 6 times 12 is 72, the denominator is 5. Okay, if you need to go back and review any of these cards or complete any of them, you can back the video up. But these are our first 5 vocab cards, or 4 vocab cards, and you're going to then attach them to your binder rings.